So just who we are, the Weights Biases, we're a startup out of San Francisco. Our leadership team is a bunch of folks who've been working in the space of machine learning for about a decade, maybe a little bit longer, each of them. They worked at a data labeling startup called Figure 8 that got acquired by Appen. And then they moved on to make Weights and Biases, and we've been partnered in our with a whole bunch of the sort of top groups in machine learning, both in research and in industry. So folks who really want to make their research pipelines and their industrial engineering pipelines reproducible and collaborative. So folks like OpenAI, Lyft, Toyota Research Institute, these are the people who were our early customers and the people who have helped shape where the tool is today. So normally I would give the story of how they came to create Weights and Biases and the sort of typical startup thing of, who are we, where do we come from? But I actually wanted to give a little bit of it from my perspective, how I ended up at Weights and Biases and why I think it's important. So I did a lot of scientific research actually before ending up here as a software engineer and educator at Weights and Biases. So when I was in undergraduate, I did work on MDMA or ecstasy and its psychological effects. And I did work on mouse brains, slices of mouse brains and the patterns of neural activity in biological neurons before going to grad school at the University of California and doing work on neural networks. So I've done research in a whole bunch of different fields. When it came time for me to do serious deep learning research, the first question that I asked myself was, what are the best practices for research in machine learning? Because if you're doing research where you're giving human beings drugs, or you're doing research where you're euthanizing animals in order to get the data that you're getting, there's a lot of important controls and organization around that research that helps make sure that it's done well. So I want to know what are best practices and expectations for research in machine learning coming from those other fields. And the answer that I found was that it was the Wild West. This was especially true a couple years ago when I really got serious on my dissertation work. I had to roll a whole bunch of my own stuff in order to track my experiments, know what was happening, and be able to recreate them and reproduce them. So if the world of machine learning and best practices for reproducibility is the Wild West, then Weights and Biases is the sheriff of that Wild West, the new sheriff in town. Maybe in less flowery words, it's a system of record for machine learning. So it solves a couple of problems: reproducibility, establishing data lineage and provenance, which data went into which models; pipeline version control, so knowing which version of software was executed with which training runs; and maintaining a central registry where all those trained models are kept along with the data. That's paired not just with this reproducibility and tracking tool, but also with tools for visualization. So we'll see some live dashboards that allow you to do quick experimentation. We also have collaboration tools in unified workspaces and reports so that one person can produce machine learning results and then other members of the team can help analyze the results of those experiments and see the results of those experiments directly rather than as, say, a copy-pasted PNG file in a Google document. And that also allows managers to manage visibility into machine learning projects across research teams, stakeholders, or if you're outside of the industrial context, maybe the academic community. Share with groups and teams and with the community at large. And then this is all supported by a modular set of tools that can be used in isolation without locking you into our platform. And these were the requests that we got from those leading research institutions and leading engineering institutions in the world of machine learning and deep learning. So those modular tools, we're going to focus on the dashboards and the reports today, but those modular tools are for experiment tracking and for collaboration and reproducibility. The other two tools in our toolkit, artifacts and sweeps, which we won't be focusing on as much today, are that model and data set registry, that centralized repository of results, and a simple hyperparameter optimization tool for organizing really large distributed hyperparameter training jobs. All that stuff is framework agnostic and environment agnostic, whether you're cloud, whether you're on premises, whichever cloud you're using, and whichever framework you're using to do your work, whether that's contemporary deep learning frameworks like PyTorch Lightning, TensorFlow Keras. We have some good integrations with Hugging Face, who do some of the best sort of open, reproducible transformers work. But then we're also integrated with LightGBM, XGBoost, scikit-learn, some of the more traditional machine learning stuff. But we're sort of a deep learning first company, and our customers are very deep learning forward people. So those are the examples I'm going to run with today. And before I go on, I want to say Weights and Biases is free for open and academic projects. If you're comfortable having your code out there, if you're comfortable having your results out there, you're free. You're using Weights and Biases is free. Using it for your personal projects, free. If you're an academic user, you can have a free account with no limits. Then there's just, if you store a whole bunch of data with us, you might end up having to pay for storage, the same way you have to pay for something like Google Drive once you get up to the hundreds of gigabytes. Then we also offer an enterprise tool for folks who are working, or everything up from a startup version of our tool to all the way to an enterprise version of our tool for people working in industrial contexts. So that's Weights and Biases in a nutshell, and a little bit of an intro and a background to who I am, who the company is. Let's dive into what the tool actually looks like. So what this tool replaces, the core dashboard tracking tool, is something like this Google Doc from my PhD research. So this is an actual chunk of the notes I took while running my experiments on critical point finding for neural networks. And you can see there's a bunch of information in here in this kind of unstructured text document way. I can barely remember what any of this refers to, even though I wrote it. And certainly nobody else just looking at this without a detailed understanding of my experiment is really going to understand what's being said here. I'm talking about run times, parameters, where I can find the data. All this stuff is in here in this Google document and then spread off across a couple of different computers in this very complicated way. And reproducing this work, when I had to go back and do it when I was doing follow-on peer review related extensions to my experiments, was a real pain. So this is something that a lot of people are doing. Actually, OpenAI, before Weights and Biases came along, OpenAI was doing something very similar. And this is no good. It's something that's not going to work for anything more than a small project with 1 or 2 people working on it. Something that's much better, even in the case of a small project like that, is a database of information about your runs, where the information about every experiment that you're running is collected and stored centrally, with all the hyperparameter information and the information produced during the run collected together. And ideally, actually, that information is accessible on many different computers. You don't want to rely on it being on one hard drive on one machine, or on some some particular place in a cluster that you're working with. That's and especially you don't want that distributed across multiple machines like I had. That made it very difficult to organize all of my information. So this is at the core, very core of Weights and Biases. This is what we're offering: a way to collect up all this information about the runs that you're doing, about the hyperparameters that went into it, and the compute config that went into it, and then also all the information generated from those runs, the loss and the accuracy, and maybe logged examples, whatever it is, all that collected together. So when it comes to things that are more complicated than just that scalar information about, oh, this is how well the model did, and this was my learning rate, and all these kinds of things, we also allow you to make these dashboards that allow you to view that data in a structured way. So information about which hyperparameters you've tried, and information about how your models are doing. So we'll see an example in just a second of a self-driving projects workspace made by my colleague at Weights and Biases, Stacy Svetlichnaya. So based on semantic segmentation. And this is just this really rich, wonderful resource for anybody who wants to understand the semantic segmentation problem that she tackled. All this information, Weights and Biases, that was generated as part of her doing this project, is now this rich information resource. So before I show you that dashboard, I want to emphasize what things you can achieve with this, whether you are somebody who manages a machine learning team, or whether you're somebody who works on a machine learning team, or shares machine learning work, research in any way. So if you're a manager of people who are doing machine learning, one of the most important things that this grants you is vision. So the ability to see who ran which models, when, on what machine, using what code on what data. So all that information can be logged automatically for you with essentially no work on your part. Then in addition, once you've built in a little bit of this integration to allow you to log results and media from your runs, you can view those results and media and the system metrics on any device from anywhere at any time. If you wake up at 4 in the morning and you want to know whether people on your team are making good use of those GPUs, you can pull out your phone and you can check it and send a Slack message following up on that information. You can also get lots of information about your model development, this intellectual property around your model development, out of things like slide decks and Google Documents, and who knows where they end up, and tie it directly to data, directly to your runs in a centralized location, whether that's in our web app on our website, or whether that's in one of our, for enterprises, we have a local solution that you can run, Docker container if you're curious. So that's something that I think people who manage large machine learning teams or work in large machine learning teams, or teams that have both data engineering and perception engineering and DevOps all together, that amount of information is super useful at the management level and at the team level. If you're, it's also useful to give you the ability to collaborate more effectively with your team, to move beyond static charts like you can generate with things like Matplotlib to interactive visualizations that are co-created by multiple people on the team and they're hooked into live data and not just, data that might have stagnated or become out of date. And it helps keep your teams focused around common goals like optimizing metrics or performance, because all that information is there for everyone to see. And it prevents people from ending up stuck in silos by automatically, instantly, and constantly sharing those results inside and across teams. So let's take a look at one of these dashboards, and I'll try and emphasize those things as we're going. So I'll also drop a link to this if you want to check this out yourself in the Slack channel. So there's just a little thread off of my talk's picture in the Slack channel if you want to check that out. Let's pull up this self-driving workspace. So this is a project that that this team member of mine, Stacy Svetlitchnaya, worked on. She worked on this when I wasn't here. And I came to learn about this project by actually looking at her, by actually looking at her her work afterwards. So the just taking a look at this project here, she logged this semantic segmentation information for a variety of different approaches to semantic segmentation for self-driving. So this is based off the Berkeley Deep Drive data set. And what she logged here was not just how these models perform. So if we take a look at this table here, there's information about how the models performed. And then there's also a whole bunch of rich additional information. So there's a bunch of tags here that I can search through, which ones of these models are ready for use in production, which one of these models were best on different categories. And then information about the actual models themselves, like which encoder they used and their hyperparameters. And then that information is also logged in, along with some rich visualizations of the actual performance of these networks. So I can take these, these are actual predictions from the networks logged along with information about how the networks did. So we can take a look at, say, this particular example here. Take a look at its predictions. And these aren't just sort of static visualizations that just show you what one particular image looked like, but you can adjust them as you want to take a look at them. So maybe I don't really care to look at that ground truth information. I only want to look at the predictions. Jumping back to that core workspace area, I can make those changes at the level of this entire project. And once I start making those changes, I'm now creating a new view on all the information for all of these projects. And this is now a separate workspace where I can dive deep into the work that Stacy has done and draw my own conclusions about the data. So I've made just a tiny change of dropping those that ground truth information from there. If I click this little button in the corner, copy it to my workspace, then I'll now I have my own copy that I can look at and adjust. So just taking a look at these examples, some of the things that I can draw from this. If you take one of the categories here is sidewalk. So looking there, it looks like this neural network has decided that this area right here is sidewalk rather than road. One might guess that maybe what's going on here is that there's a human walking here in this area of the road. There aren't humans walking in that area in the center where the network is identifying a road. And so in this area, possibly because of the presence of the human, the network has decided that that area is probably sidewalk. It's also correctly identifying some areas of sidewalk on the side of the street. So that suggests that maybe there's a lack of examples where humans are walking on things not sidewalk in our data. So I might add a note or a tag on this run about that information, and then my teammates can come in and see that information and check those results. Let's see. I think maybe another useful thing you can do is there's a search for particularly interesting runs. So the more information that your team logs, the more that you can find here. I think one interesting one that I found that she logged was this best human IOU run. So this best results on the human class, which is pretty important for self-driving, being able to detect humans. So she logged a bunch of results from this one. And the interesting thing about this particular example is that you can see that the predictions are much blockier. So this best human IOU example has these very blocky predictions to it. Whereas if I compare that to one of the other examples, let me just type the word best here to filter down to the best examples. And pull out maybe the ones with the best car accuracy and the ones with the best human performance. Or that one. Yeah, that one. So now I can compare the outputs of these two, and you can see really clearly that that these networks have learned something very different for their semantic segmentation. One of the two semantic segmentations is much cleaner, is much the like pulling out these say these power lines in the background here, or this building in the background here is done much more cleanly by this one that got the best accuracy on cars than the one that got the best performance on the human class. And so now that I've pulled up these two, I'm curious, okay, so what makes these two examples different? So I can see a little bit of these logged metrics here, things that Stacy thought were important to note about these. I can also, I'm curious now, how are these two examples different from each other? So I just popped up a new chart here. And I can take a look at the differences in the information about these two runs. So there's lots of differences in here. Maybe I'll make this a little bigger. There's lots of differences in here. It looks like they trained for or ran for different amounts of time. Looks like we can see that there's that different results where the car accuracy is higher for one than for the other. But the biggest parameter-wise difference here appears to be this ResNet versus AlexNet for the encoder. So using this older AlexNet encoder for the images as a sort of pre-trained network seems to give us this blockier result here. But interestingly, gives us better performance on the human class. So these are all things that can be learned just by looking at all this information logged about these runs. And I just want to compare that to the stuff from my from like the stuff that I logged when I was doing my PhD work. I logged this information in I wrote information about this stuff in a Google document, but it was not well organized, difficult to read because it's not systematic. And so the systematization that logging provides gives allows you to do a much better job of collaborating with, whether it's yourself in the future or with the other members of your team. So that's the dashboard piece of this tool. So again, everything about that, as long as you can just pip install WNB, sign up for an account, and completely free, and you can make dashboards like that for your own projects. And so there's lots of our users really like this toolkit and have written about their experiences using this toolkit. So I've got some folks from the ETH Zurich group. There's some folks who do climate related research there. They use deep networks to pull out extreme weather events from I believe satellite imaging information. And they talked. They use weights and biases for experiment tracking and collaboration, and they found a lot of benefits to using this tool. They being able to access the entire project history from anywhere at any time, being able to watch every experiment unfold in real time and not have to catch people up on what's going on, and being able to focus on discussing on next approaches instead of spending all that time catching up. So they wrote a little bit about their experience using weights and biases. So we got lots of academic groups, lots of labs around the world, not just the big ones like OpenAI. We're using this tool. So that's the dashboards piece of weights and biases. The other piece is so those dashboards are kind of like this live place where the information is streaming in from your runs as you're doing a bunch of different experiments. Once you've got all that stuff there, you can live edit it like I was just doing if you want to take a new view on your data. But when it comes time to actually report your results, a big dashboard like that is maybe not always the exact thing that you want. And so then when it comes time to report results, a lot of people report their results as just tables. They'll take the final outcome of their experiment will be like a couple of figures and a couple of tables where they're claiming, state of the art for their performance on some data set according to some metric. And there's this gets the information out there, but there's a lot of things that aren't so great about this way of presenting results. Like, for example, just looking at this table here, it's attached to a paper. Looking through that paper to find information about just exactly what all these models are, what these things mean, and what code was run to generate them is often very non-trivial. So understanding enough information to be able to reproduce work that somebody else has produced is something that's often quite difficult based off of the way information is shared in academic papers. So this is not great. Something that would be much better is if all that rich information that you're generating when you're running your experiments is tied to your visualizations, is tied to your output results, so that, and especially if it's interactive, so that people can come in and take a look at those results and maybe do a slightly different analysis. Take a look at your results and say, what would happen if I took the mean instead of the median, things of that nature. So that's what weights and biases reports do. Another way of thinking about why something like this is necessary is that in other, it's well recognized that static documents aren't really sufficient for communicating results in lots and lots of domains. And the common solution to this is to use computational notebooks to communicate results. So the issue with that for ML experiments is our experiments have compute needs that are way too high. You might need to run for weeks or months in order to see the results that somebody saw. So reproducing the results all the way from the beginning, from scratch, isn't a great way to requiring people to reproduce your results from scratch isn't a great way of allowing them to engage with your work more directly. So the result, or the way around this, is to integrate those experiment databases into your results. So rather than having people reproduce the production of all that information, share the information with people, and then that and then they can take a look at the output of your runs to sort of reanalyze them. This is maybe something that's not that uncommon in other disciplines like biology, where somebody's going to have a real tough time recreating your experiments. Putting that data up there is a much better way of letting people feel confident that your results are good or that they understand your results. I'll go through a quick example of what a report looks like in weights biases, how you can generate it, and use it to communicate your results with rich text, with media, with interactive charts, and more. So we'll go through that in just a second. I just want to say a little bit about some of, before, it's not just, my opinion that reports are a good tool for collaboration. This is something that the sort of power users of weights and biases are, have shared with us. So one of those users is Alex Pino, who works on the robotics team at OpenAI. They've essentially shifted exclusively to using weights and biases reports for their workflow as their means of sharing results. Mixing real data from experiments with context and commentary is what really makes it work for them. This is straight from the horse's mouth. They did used to create Google Docs for tracking all their information in a line of experimentation, and the bookkeeping and the data sharing made that workflow not scale well, and made it a pain point. And so you can read a little bit from Alex on how they used weights and biases reports in the Rubik's Cube solving robot project. So OpenAI Robotics did this cool dexterous manipulation research project with a robot that could solve a Rubik's Cube. And so he also wrote in this little report on how they found the best practices for using reports. Another group of power users of weights and biases are at Latent Space. They work on a differentiable renderer, so a graphics rendering system that's based entirely around neural networks. And the folks at Latent Space use weights and biases and reports as a way to share results and build on top of each other's work. They found it really difficult to build on top of each other's work without some of these features, and especially the reports, which they use to make sort of draft pieces of papers that come together at the end. And so she wrote a report about how she used the weights and biases tools to debug a GAN. So how to detect an issue with one of their generative adversarial networks, notoriously real tough to get working. So they used some of the logging tools and weights and biases to get that, to resolve that issue. So let me just show you that this demo here. I'm going to build a little report out of a hyperparameter sweep that I did on the MNIST data set. So let me copy that link and pop that open. Okay, so this is a collection of results from an experiment I did when I was getting to know how to use the tool when I first joined on the MNIST data set. So I wanted to do a big hyperparameter optimization sweep on this data set just to learn the ropes of the tool. So this is one of the first things I did. And so this visualization here shows all the runs that were in this big hyperparameter optimization here, this parallel coordinates chart. This is a really nice type of chart for visualizing hyperparameter optimization. So there's, I had never seen it before, but it's actually something you can find in a couple different visualization libraries. So I'd recommend using this to visualize your hyperparameter optimization results, whether you're using weights and biases or not. But this parallel coordinates chart here has each column is a different hyperparameter. And so this first column here is which activation function is being used. And so tan H, soft loss, sigmoid, all these different activation functions. Then each line here represents a single experiment. So this is one experiment where I optimized a neural network on MNIST. And this one happened to have the tan H activation, which I know because it goes through the activation column at the tan H point. And this one has soft plus, sigmoid. It also passes through all the other columns at the point where, so this one had a batch size of 8, so it passes through the batch size column there at the height 8, and the learning rate column at about 1e minus 3.
And then these lines are all colored by how well they did on the validation loss. So just taking a look at this experiment, the first thing that I saw was that there's a lot of runs that are producing these like absurdly high values for the loss, like 10 to the 16, which is an absurdly high value for the cross entropy loss. Should be like 2 or 3. And then I also had a bunch of runs that were producing values that were either, minus infinity, nan, null values, all kinds of issues happening here. So there's something that's not going well in my ML experiments, and I want to figure out, what's wrong with it. So I can, the way to do that so I could drill down in this the same way I was drilling down in that self-driving car workspace earlier. But what I'm going to do instead is I want to, build a specific view into this data that drives a particular insight about why these NANs are happening. And then I want to be able to share that with other folks on my team. So what I'm going to do instead is build one of these reports. In this report, I can add markdown, images, LaTeX, things like that to it. So I might write here, looking into what's causing NANs here. And then I'm going to start drilling down here. So these visualizations here, they're attached to these collections of runs, so that you take a big collection of runs and then turn it into one of these visualizations. So what I want to do is focus down in on the runs that are causing problems. So down here, this is a table. It's got let's filter this table down to the runs that are causing issues. So that's the ones whose validation loss is nan. So let's name this view of our table here as runs with nans. And just looking at this now, it's focusing down so I have the same visualization, but it's now been regenerated with just the runs that produce nans. So just taking a look at this, it looks like one big issue is this parameterized ReLU activation function seems to not like something about the way I've set up this neural network. So this parameterized ReLU is not working super well. And then it's also happening when the batch size is low and the learning rate is high. So you can see these lines are all curving here from low batch size to high learning rate. So that suggests that this combination is particularly bad. It's maybe also useful to, let's maybe clone that bad boy. So it's to also look at the runs where they had really high loss. So a reasonable value of this would be like 2 or 3. Let's just look at the ones that are bigger than 5. So I'm building up this visualization here. Let me name that runs with high loss, and I can see the same pattern. They also maybe a little bit less common from the parameterized ReLU function, but from some of the other functions, the other activation functions, I'm getting the same result. That low batch sizes and high learning rates are the problem. So let me just write a little note. Looks like it's high LR and low batch size. Training instabilities, that might be the cause. So I've started to sort of get this insight down, and I could drill down even further and see what's causing these issues. But instead of continuing to edit this thing, I'll just show you what a final version of that report might look like here. So I spent a little bit more time making this look nice here. But that's that same visualization we were just looking at with things that had poor performance, whether that's losses or nans. And then I took a look at the gradients, which I'd logged also along with these runs. What were the gradients of all the weights and biases of my neural network? And I can see that for the ones that failed, the gradients go from reasonable values near 0 to really, really large values in the thousands. So training's blowing up, and that's just instability from having high learning rates and small batch sizes. That's a bad combo. Looking at a run where that didn't happen, I can see the gradients stayed small all the way through training. So this is a successful run. So a run with a low loss and no nans. So these are the kinds of things that these reports let you do if you instrument your stuff with weights and biases. Just FYI, we are in fact hiring folks. We're looking for back-end engineers, front-end engineers, software engineers, folks in sales and growth. We have a big presence in Armenia. That's how I found out about DataFest Tbilisi, actually. So if you're in Central Asia, Eastern Europe, we've got a lot of folks in your time zone doing stuff.